Yes, so in the last class, we saw that in the high Reynolds number case, we got an equation where there was no viscous term. Okay. So basically, it was the same as putting mu is equal to 0 or neglecting the viscous term, right? So, but the resulting equation that we got, only one boundary condition could be applied, right? For the first order equation, only one boundary condition could be applied, and it can't satisfy both the no slip and the specified velocity far away. So, inviscid approximation can't be valid everywhere, no matter how large the value of the Reynolds number, right? Because the no slip condition is discarded. So Pradel came up with the boundary layer concept, and in that boundary layer concept, it contains scaling assumptions that are incorrect in the vicinity of a solid object, right? Because we need a second order equation to satisfy two boundary conditions, and hence in the boundary layer, viscous stresses are important, and outside the boundary layer, not so, right? So today, like we'll be exploring that also. Okay, so by the way, like turbulence part, I will be covering the lecture 13. Okay, so there are only 12 weeks of lectures, but there is an option to have an extra session, right? So in that session, I'll be covering the turbulence part. Okay, coming back to this, say for the laminar flow condition, but with high Reynolds number. So this is our solid object, and fluid flows around it like this. So basically, what Prandtl proposed was that at the very close to the surface of the solid object, okay, throughout this solid object, there is something called a boundary layer, which is the inner region, and the implicit approximation holds true in the outer region. Okay, so let us do something interesting. Okay, here that same high Reynolds flow laminar case. Let us first write down the equation. So we neglected the viscous term, right? And we got this kind of equation: rho into substantial derivative v by dt is equal to minus dynamic pressure. We get into the dynamic pressure. Okay, so let's check. It's already the high Reynolds number. You're taking it as inviscid. Okay, so that is one approximation. Let us also consider the steady state. That is rho by dou t is equal to 0, and rho is equal to constant, uniform properties of the fluid. Okay, so it will just be rho v dot del v plus del pd is equal to 0. Let us dot this with velocity vector. Right? Say divide throughout by rho. Okay, so there will be a manipulation of this V dot del V. Okay, it's okay, let me everywhere I don't need to put this arrow sign. It's understood that it's a vector. So this is a mathematical expression. Okay, so V dot del V is equal to V dot. I'm not getting into the maths of it, okay, but just know that this is equal to zero. This is not a vector algebra class, so I'm not going into this details. Even divergence curl and all, like I just touched upon very briefly. So this just you take for granted or refer to any maths book. Okay, so our equation will reduce to V dot that earlier equation del V square by 2 plus del PD by rho is equal to 0. Okay, if we take rho out, del outside, so it's V dot del of V square by 2 plus PD by rho equals 0. And PD is the dynamic pressure, right? Let us break it into the normal pressure, the gravity term. Okay, so say this is some component, this is some quantity B. So basically this reduces to V dot del B is equal to 0. Fine. Substantial derivative of B. This is steady, so it's already 0. And so this substantial derivative dB by dt is equal to V dot del B. It basically means that, say this is a streamline. In this streamline, delta B is equal to 0 or B is equal to constant. Okay, so V square by 2 plus P by rho plus GH is equal to constant along a streamline. What's the assumption being that it's a steady inviscid flow. So this is what is the famous Bernoulli's equation, right? That for steady inviscid flow, V square by 2 plus P by rho plus GH is equal to constant along a streamline. So these three terms are the kinetic energy term, pressure work term, the gravitational potential energy. Okay, coming back to the boundary layer concept. So basically, like if you remember the figure I drew earlier, the outer region is the inviscid flow. Inner region is the boundary layer. Considering the case of laminar flow at high Reynolds number. See, even Reynolds number of 5, 10, 15, 20 is high. It's not like Reynolds number has to be 2000 or 3000 to be high. See, basically, what is Reynolds number? It's a measure of the inertial forces to the viscous forces, right? So, if it is 1, you can say that inertial forces are comparable to the viscous forces. While if it is much greater than 1, say 5, 10, 15, 20, the inertial forces dominate over the viscous forces. So, even that is high Reynolds number. It's not that it only has to be 2000, 3000 for it to be high. That is like different case altogether. Okay. So, coming to the boundary layer concept, let us non-dimensionalize Navier-Stokes equation for high Reynolds number. So just check the notes of the previous class and write the non-dimensional Navier-Stokes equation for high Reynolds number. We did it in the previous class only. I'll just give you a couple of minutes to go through your notes and write down the equation. See whether this equation you got from the previous class, Reynolds number into substantial derivative velocity dv star by dt star. Our pressure scaling was this, right? Delta star dt star plus delta star square d star. This is of order 1. This is also of order 1. Likewise, this is of order 1. And we saw that Reynolds number tends to infinity. This term and this term must be similar, right? And the scaling that we obtained was phi is rho u square, right? Okay, so to that regarding the two boundary conditions thing, with only one being satisfied in case of a first order equation. So Prandtl came up with a solution. Okay, just remember this very famous name. So he was a very famous German fluid mechanist. Mostly in fluid dynamics he used to work. With his students, very famous ones are Blasius. You learn about it in boundary layer, and von Karman. Again, that also in boundary layer. Okay. So Prandtl also has a very famous equation, number in non-dimensional number in fluid heat transfer, right? Familiar with this Prandtl number, which is the ratio of momentum diffusivity to the thermal diffusivity, alpha, which is nothing but K by rho Cp. Okay, so what Prandtl told was that instead of doing it like this, because like in this case it is reduced to a first order equation and you can't satisfy two boundary conditions, he told that write this equation in this kind of form. dv star by dt star is equal to minus del star pd star plus 1 by Reynolds number delta star square p star. And what he said was that you say that to that make this equation make sense, you tell that this delta star square v star is of the same order of magnitude as Reynolds number, right? Then this equation will be logical. This happens, then you can say that 1 by Reynolds number into delta star square v star is of order 1. The region in the fluid flow where this is valid, that is a momentum boundary layer. Okay. Likewise, there can be boundary layer for heat and mass transfer as well. Basically, in the boundary layer, the viscous forces are comparable to the inertial forces. Okay, let's take a small break and then I will come back to the boundary layer concept. So if you remember, there is a fluid flow around a solid body. Okay, there is a fluid flow around a solid body. This dimension of this body is L, and there is a boundary layer of thickness delta X. You can refer to Sir's lectures. Okay, so this is Y direction, this is X direction, V component velocity, U component velocity, delta X in Y and L in the X direction. Okay, and there are two velocity components also, V and this is like the boundary layer thickness. Say this is the dimension in X direction. At some X, you'll have a boundary layer thickness of delta X. Fine. And this delta is much, much smaller than L. So there are two different length scales, L and delta. Continuity equation goes as this: 2Vx by 2U plus 2Vy by 2Y is equal to 0. So let us just replace this Vx, UV, etc., Uy in terms of the length scales and the velocity scales. So this is first term is of the order of V component of velocity, so U by L. This is of the order of V by delta. Okay, so obviously from this equation, U by L should be of the same order as V by delta. But since U is much, much less than V, L should also be much, much less than delta, which was greater than delta. So as Reynolds number tends to infinity, the flow inside boundary layer approaches unidirectional flow. Okay, let us now look at the x component of the Navier-Stokes equation for steady state. Component of Navier-Stokes equation. So it's Vx do Vx by do x plus Vy do Vx by do y is equal to minus 1 by rho do Pd by do x plus nu into 2 square Vx by 2x square plus 2 square Vx by 2y. And pressure scaling term, it goes as, since Pd goes as rho u square, x goes as L, so this goes as 1 by rho u square by L. So u square by L. So let us do the similar like this. What is the order of each of the term? So this first term's order is like u into u by L, so u square by L. This is u into v by delta. Right. This already we saw. It goes as u square by L. Then these two terms they go as nu into u by L square, nu into u by delta square. So since v by delta is equal to u by L, so this we can also write as u into u by L or u square by L, which is same as this one. because it's high Reynolds number case, like obviously this nu u by L square. Here there is u square, here there is only u. So this term you can neglect, take it as 0. So basically what are the terms you have? You have u square by L, u square by L. Pressure scaling is also u square by L. Here you have nu u by L square. This goes as 0. And then another term, this term is nu u by delta square. Okay. So this can be equivalent only if nu u by delta square is of the same order of magnitude as u square by L. So u gets cancelled out. Or delta square is equal to nu L by u. But Reynolds number, we already know that Reynolds number is u L by nu. So multiply both these sides. This and this you multiply, this and this you multiply. So you get Reynolds number into delta square is equal to u L by u. This gets cancelled. This gets cancelled. You just have L square. So Reynolds number into delta square is equal to L square. Or del square by L square is equal to 1 by Reynolds number. It just implies that delta by L goes as 1 by root over Reynolds number. So if Reynolds number is very high, it means that delta is much smaller than L. Right? If you take an example of a case where U is like 1 meter per second, length scale is 1 meter, and you have the fluid medium is air. So a Reynolds number will go as 1 into 1 by mu air. Or now you put this equation, delta will go as square root of the kinematic viscosity. Okay. So in the case of air, this quantity is 10 to the power 5 minus 5 meters square by second. So our boundary layer thickness will be 3 millimeter. Okay. So basically for 1 meter per second fluid flow velocity, length scale is 1 meter, your boundary layer thickness will be just 3 millimeter. And we already know that V by U goes as delta by L, and this is 1, this is 1, this is 1, this is 3. So V also, that V component of velocity will go as 3 millimeter per second. So U component is like 1 meter per second. So just go through this part once and see if you are convinced with the argument. So I will just add some more points here, okay? We already saw the concepts of curl, vorticity, velocity, potential earlier. Okay. And then also stream function. Remember psi for 2D. Okay. Then we got Laplace equation, right? Remember Laplace means just del square of that is equal to 0. And I also told you that potential flow is inviscid plus a rotational flow. So if Reynolds number is very high, it's usually irrotational. Most inviscid flows are irrotational. Also take the curl means del cross, okay? Curl of Navier-Stokes equation that will give you the vorticity transport equation, which goes like this. Okay. And this will be like zero if Reynolds number is very high. So essentially like you'll take the inviscid flow case. So in case of steady state, it just reduces to V dot del W is equal to W dot del. Okay, anyway, like let's go back to, I'm just digressing a lot, I think. Let us go back to the boundary concept. I'm not going to the details of vorticity transport and all. So basically we had two flow regimes. In the outer region, we had potential flow, and we have a boundary layer in the inner region. Okay. So basically we have differential momentum equations with different scales. We join the regions to get a smooth solution. There is a sequential scheme here. We first solve the outer problem to the one boundary condition, and that result is an input in the boundary layer problem. Yeah, I think I'll wind up the class here.